Okay. Hello everyone. And I just want to make sure you are hearing me well. And if you can't hear me, just tap your screen to unmute your speaker. Okay, very good afternoon or maybe good morning. Welcome to our today's live webinar to learn about how developers implement ClickHouse in ByteDance and what improvements we have made in ClickHouse. And today we have two presenters. The first one is Yiyang Shao. You could say some words to our audiences. And the second one is Zhao Jianyu. Yeah.
Hi everyone. Yeah.
And Zhao Jie.
Oh, hello everyone.
Yes. And both of them are engineering from ByteDance. And the first one, they will give us a talk for about 40 minutes. And before we get started, I just want to remind you, and any questions and comments on their talks are welcomed. And please type them on the chat box. Okay, let's move on. First, that is welcome Yiyang with his talk. His talk is about how to speed up data analysis with ClickHouse. And in his presentations, he will go through the basics of ClickHouse and the use cases of ClickHouse within ByteDance. So, okay, Yiyang, are you ready for your sharing?
Yeah, sure. Let me just share my screen. Okay. So hi everyone. My name is Yiyang, and I'm working at ByteDance Data Platform Department, and I'm based in Singapore, developing ClickHouse. So today I would just want to give all of you a quick introduction about ClickHouse and how you can leverage ClickHouse to speed up your own data analysis use cases. Okay, first of all, let me introduce something about analytics. So with the trend of big data, people start to wondering how we can, generate insights and harvesting those data to create value from those big data size. So analytics become more and more common and popular. Therefore, there's a new concept called OLAP, online analytical processing, comes into people's vision. So OLAP will sit inside a data pipeline or a data system, become an add-on to the traditional transactional database. You can see from this diagram, so the transactional database will still process all those daily data processing, like your ATM transaction, your e-commerce ordering, your hotel or flight booking. And then they will store all centralized stored in a data warehouse. But OLAP now comes into the place as a role for analytics. So the OLAP system will process all those real-time or historical data, combine them together to provide insight for the presentation layer. So you can have your business intelligence, your reporting system, your data visualization, and even some of the more advanced data mining use cases. So it's because it's quite different. It's a quite different use case. So OLAP sometimes have a very unique characteristic. So for example, OLAP usually requires some complex query compared to transactional database. Usually just try to read precisely with several rows of data. And it also involves computation like aggregation over certain dimension and then group by certain dimension. And it's multi-dimensional. And the requirement for the read is actually more intense than the write. So for an OLAP system, you will need less frequent update, but you will focus more on your select query. You want the select query to be fast and processed in real time. So to solve this use case, people start to develop dedicated DBMS for analytics. Actually, starting from the beginning, people are just actually using the normal transactional database like MySQL and try to do some add-on development work to make it usable for analytics. Then we have dedicated DBMS like Killing and Presto. So they typically being divided into two types, and of course there are other types, but these two are the mainstreams of OLAP. One is called multidimensional OLAP engine. It usually involves certain pre-computed cubes, so it can handle larger data size and larger like more complicated queries. But it will have its own limitation. For example, because we need some pre-calculated results, so the dimension is limited, and the query pattern needs to be relatively fixed. So people start to explore an alternative. People start wondering how can we get the result in real time and precisely. So Presto, things like Presto, Drit, or even some other system become into a OLAP system, which no pre-computation will be involved, and all the data result will be calculated in real time. So besides these three or two main categories, we have a lot of like products and business solutions in the market. Some of them are hosted in the cloud, like Redshift, BigQuery, Snowflake. They're easy to use, easy to hands-on, but they are cloud dependent, and sometimes it cannot require to fulfill some on-prem requirements. And we also have like legacy database, just like MySQL. They are not designed for analytics. And we have the Hadoop system, ecosystem. So Hadoop, Spark, this kind of non-SQL but solution, which usually involve intensive computation resource and slow response. And we also have some domain-specific solution, things like Elasticsearch, InfluxDB. So Elasticsearch is catered for non-structured data, especially for text search, log search, but they are complex to use and sometimes not easy to handle because it also requires some domain knowledge, like Elasticsearch SQL to query the database. So however, today I just want to present you guys another alternative, which is ClickHouse. Let's take a glance at all the ClickHouse features. So first of all, ClickHouse is designed for analytics. So it's super fast. It is even faster, like 100 times faster than a typical DBMS, and it is claimed to be 100 times faster than the Hadoop system. And secondly, it's like a SQL-based, SQL-compatible DBMS. So it will have no steep learning curve to get started. And it also comes with like rich features, like rich interfaces, rich data types, and table engines. All those data types you are familiar with, you will be able to use them in ClickHouse. And ClickHouse also has a share nothing architecture, and with its replication and with its replication, so it mechanism, so it can achieve like nearly linear scalability and reliability. And another good thing about ClickHouse is like it's open source since 2016, and it's under Apache 2.0 license. So you can use it for free and quite flexibly. And last but not least, it does not involve any Hadoop ecosystem. So you don't need to get into the hassle for setting up the Hadoop system, and you can just use ClickHouse right away with a single binary. So this is an official benchmark on ClickHouse documentation. So you can see compare with Vertica and Greenplum, which are also popular in the analytical space. ClickHouse can easily achieve like tens and hundreds times more performance in all these standard common scenarios. So that's why we start to adopt ClickHouse at ByteDance. So because in ByteDance from the beginning, we want to have some OLAP engine which can be shared among, which is like a reusable component which can be shared among all different data applications and business lines. And we want to achieve a QPS up to 100%, up to 100 and plus. So with this low latency. And we also have quick application setup to be easily administrated, and also sub-second response time. We want like a real-time analytic engine, and we don't want to have any pre-computation. We want all the data to be real-time data. So right now, after several years of development, ClickHouse has already been supporting 80%, over 80% of analytical applications in ByteDance. For example, like CDP platform for the ads department, and also our user growth tool and our A/B testing tool, and even some our algorithm optimization for the recommendation. So if we go into a bit detail about the CDP use case, so CDP usually involves like user clustering, user portrait. So with ClickHouse, we have been able to support over like 1 billion traffic stream, and with our special optimization of like bitmap data type, the whole platform can reach to a QPS over 200. And we can easily process like 200 million user package. So we can support up to 200 million users. And all the queries can be returned within 5 seconds. Second example is like in our Douyin events. So we host a lot of like online Douyin events. So sometimes it can get like a huge traffic peak. But with ClickHouse, we are able to manage like 2.5 million insert TPS. So the data can be right in real time and stored in real time. And for the activities during this live event, for example, like red packet, like gift, lucky draw, all the analytics can be returned within 0.1 second latency. And this data is based on like 200 million live views, and we are able to process like 70 million user comments, and harvesting from this 70 million comments like that they're written by users in real time to generate like hot topics and then push back to the users during these live events. Last but not least is our like famous recommendation machine learning model. It is also trained on our on the ClickHouse cluster. So they have already been using like 200 plus nodes, and they are processing 10 plus petabytes data. They are using 10,000 queries per day, and with a 350 terabytes data growth. So that's all the that's several examples of how we use ClickHouse in ByteDance. But you may be wondering like why the ClickHouse can support this large amount of data processing and give the analytical results in sub-second or even just several seconds of time. So let's take a simple look from a sample query. For example, this is a very typical analytical query. So you select certain columns and you count distinct for another matrix from a table, and you have some filtering conditions, and you group by C1 dimension. Okay. So this is quite typical analytical SQL query. So how we process this query fast? The first step is we need to read fast and try to read as less data as possible from the disk. So first of all, the ClickHouse uses a local attached storage. So by using a local storage attached storage, the data is closer, is the closest way to the CPU. If we don't count memory, because so memory is not a persistent storage, but local attached storage actually is the best way to make the data closer to the computation resources. Secondly, actually, ClickHouse uses a partition. So for example, if we have this table 1, we partition it into date. So every data point are split into partition by date. So if we query from 1st of June and to 7th of June, we only need to select these 7 partitions. Okay, even though you have maybe stored like 2 or 3 years of data in this table 1, but it can quickly locate these 7 partitions. So in this way, we achieve the read less. And also, this ClickHouse has its unique column-oriented storage. So in ClickHouse, the data are not stored in row by row. It is actually stored in a column fashion. So just to give you a quick visualization on how column storage can help the analytics use case. So if the data is organized in a row-based fashion, for the query we see just now, it needs to read all the columns for all the rows that involved in the computation. But for a column-based database, it only needs to read the part of the data that involved in the query, and only the columns of those part of the data. So it makes the read the data read like less and also fast. And because of this column oriented storage, the ClickHouse can do even further optimization based on this. So we can achieve a better data compression rate. So the data sit on the disk becomes smaller. So because of this, when you read through it, the read data also becomes smaller. So less disk spin leads to less time. So the compression algorithm used in ClickHouse is actually quite straightforward. It's just a very common LD4 the STD compression algorithm, but because each column has exactly the same data type, the compression rate can actually reach a very good result. And then it's about its indexing. So in ClickHouse, for each table, we probably need to we need to assign some order key, which can also serve. You can understand it as a primary key in other databases like MySQL. So the data is sorted according to these order keys. So for example, if your where condition includes one of your sorting key, like C1, so it will first try to find the block of data that containing 10, the number 10, and it will only read from that block. So it will automatically ignore all the block like before this block, because all the data before this block are smaller than 10, for sure, because the data has already been pre-sorted. And even more for each block of data. So by default, the data is being organized in a granularity of 2,192. So for each granularity, you actually only need to read one row of that data, because you just need one flag to tell you the data range that you need to read. So it will also make the read more efficient. And moreover, we can also incorporate with like secondary index for specific data schema to further accelerate the read process. And another thing is about like later materialize. So we have this pre-where clause. How it works? So because C1 larger than 10 is one of the condition. So it will only read through the rows that satisfy this condition. But when the ClickHouse knows that you have this filtering, it will also ignore all the unrelated data in column 2. So because you add this filter for C1, it actually also works on C2. You also read less data in column 2. And beyond all of that, all of those optimizations, ClickHouse is trying to incorporate, parallel read in multiple threads, and also you can optionally assign a parallel read among replicas and nodes. So if you have a multi-sharding cluster, the ClickHouse will try to assign, the data block that need to be read into two replicas or more replicas. So you can read together and then aggregate, merge the data together. It will also accelerate the data read time. So after the first step is a ClickHouse engine, like the reading process of the data engine. Then it involves into the process part. So in a typical analytical use case, we will do sometimes quite complex aggregation operations. For example, just now we have a count distinct function, and sometimes you need to do sum, you need to do average. So this comes to the processing part, the computation part. ClickHouse also did a lot of optimization in the computation part. First of all, it's a C++ code base. So unlike some other Java-based Hadoop ecosystem, the code itself is optimized to the extreme. And ClickHouse also incorporate like vectorized execution. So like SIMD, it supports like SSE 4.2 plus. So it makes a block of data, because based on its like column-oriented storage, it can incorporate its vectorization even better. And thirdly, it's a share nothing architecture, just like I mentioned before. So with this MPP architecture, it can achieve linear scalability, and it can massively parallel its threads to process the tasks. And lastly, it's actually another unique point of ClickHouse. So the author of ClickHouse and the community of ClickHouse are trying to optimize as many things as possible, even for very small details. Just give you an example, like the algorithm for the group by operation in ClickHouse. The community actually incorporate like tens of different algorithms just for different types of data type. They will choose the best algorithm for that specific data type. So based on these details and the overall architecture and some like small details, the whole ClickHouse engine actually can process the query super fast and faster than most of the DBMS you have seen on the market. Okay, and then I think I will give a quick summary of my talk. So ClickHouse is an open source OLAP DBMS. It has been developed since 2008 and open source in 2016. It has a very efficient data storage, as I explained. It has a column-oriented storage to achieve better compression rate and faster data read speed. It also have very efficient data query, like primary index vectorization, multiprocessing, and distributed queries. All these kind of optimization and pay attention to code details makes the ClickHouse engine computation super fast. Lastly, it actually involves everyone. So it's not only about the data engine itself. If a data engine can only run fast, but you cannot integrate with it, you cannot use it easily, then it doesn't mean anything. So ClickHouse has its own flexible integration. So it is SQL compatible. It provides like JDBC connection. It provides TPC, HTTP, any interface you can think of. And the data is actually stored in a relational fashion. So unlike like other things like Elasticsearch, you don't actually need to change too much on your existing data table schema. So, and you may wonder after all of this, how should I choose? When should I choose ClickHouse? When should I choose other things like MySQL, Greenplum? Okay, just give you some hints on how to choose ClickHouse. So if you have a large amount of batch insertions for your data writing, and you do not have very strict requirements on modification of data, and you can accept that you combine all your small tables into a wide table for query. And most of your daily query are involving like aggregation computation of selected columns. And you want like really fast select operations. Then please don't hesitate to try out at least ClickHouse. And some use cases that you actually should not use ClickHouse is that if you have a traditional transactional processing use cases that you think update and transaction guarantee is a must, then skip ClickHouse. Or if you have a requirement for like key value storage that your query is usually just looking for a single data point among your whole database, then ClickHouse is not suitable for that. And then if you have a like almost over normalized data, which you have already split your data into multiple tables, and for each single query, you will also require like several joins between tables. Then ClickHouse is not suitable for that. ClickHouse prefer a wide table with like many columns. And lastly is like blob and document storage. So ClickHouse is simply does not support that. So hopefully this chart and these points can give you a starting point on deciding how if you want to start to try out ClickHouse. But if your use case satisfies the left part of the table, feel free to do it, and you will never regret about it. Yeah, I think that's all for my sharing today. I will hand over to Zhaojie to introduce more on how ByteDance actually modify the ClickHouse to serve better.
Okay, thank you, Yang. Thanks for your presentation. And you could have a cup of water and have a rest. And
thank you.
Yeah, and just a reminder, I have noticed that there are more and more people coming into the live stream rooms, and I just give you a reminder that you guys will receive a survey and please in the chat box, and please fill out the form to help us improve our next webinars, and your suggestions are highly appreciated. And then now we will welcome Zhaojie. He will give us an introduction to Cloud Native ClickHouse, a new data analytical engine developed by ByteDance. And first, okay, welcome, Zhaojie.
Hello everybody, and thanks Yang sharing. And my name is Zhaojie, and today I will introduce our new system. So when looking at this title, somebody may want to ask there are many kind of cloud native ClickHouse. What kind of cloud native ClickHouse will you introduce today? But I want to say, oh no, this is not a kind of cloud native ClickHouse. It's really a name of our new system because internally we call it CNCH. Let's start. Yeah, this is the outline. First, I will introduce some background and the motivation why we start with this new system. Then I will give some overview of our new system as well as the implementation details. Then I will list some future works, and at last I will summarize today's sharing. Yeah, let's start. So before I introduce our new system, let's take a look at the existing architecture of the ClickHouse. So ClickHouse is using a shared Latin architecture. The computing resource and the storage resource are tightly coupled, as shown in this figure. So you will notice each machine has its own data, so the data are not shared across different servers. So that is why we call it shared Latin architecture. And this architecture has some pros and cons. And its advantage is it's super fast in the local machine. In theory, the limitation will only be the hardware resource of this server. And but this architecture has some has two major disadvantages because we know the computing resource and the storage are tightly coupled, which means they cannot be scaled independently. For example, if sometimes we don't need so many computing resources, but in order to make our data is always available, then we still need to have those servers, even they are not being used efficiently, and which means we will have some waste on the resources. And so this is the first disadvantage, and it has bad elasticity. And the second one is because data cannot be shared, as you then for example in this figure, like the data A cannot be shared by other servers. So even when the other servers are free, then we can still not utilize those computing resources. So it means it has bad scalability. Then let's take a look some real story internally. And so in ByteDance, the application is expanding and changing extremely fast. And so it means we need very strong requirement on the cluster scaling. Let's take a look at two cases. First one is let's take a look at the first case shown on the left. For example, if sometimes at some moment, like class 2 require more resources, but class 1 don't need so many resources, then actually the class 2 can borrow some resource from class 1, right? But actually, for example, we can move the two machines from the class 1 to class 2. But the challenging is the data. These two servers have its own data. So which means before we move it to class 2, we need to move the data C and D to the other servers in class 1, and then we start the movement. And when the two new servers comes to class 2, then in order to utilize them, we still need to rebalance some existing data in class 2 to these new servers. You will notice it has a very high cost on the server movement, which means we have a lot of overhead on the data movement or rebalance. So sometimes we cannot we will miss maybe the best time to do the cluster scaling on time. And let's take a look at the second case shown on right. So instead of moving the server, sometimes we want to migrate some applications to some other cluster. For example, like we want to move the one application from class 1 to class 2. So which means first we need to move its own data first, right? So means we need to have we have to utilize some tools to do the movement, like from class 1 to class 2. And so you will notice from these two real cases, the migration cost is very high on the shared Latin architecture. So the question comes, so can we utilize the shared storage architecture to solve this pain point, or even can we support the shared Latin architecture natively by taking those questions in mind, we start to explore some new architecture for our internal ClickHouse. And so we start to consider the shared storage architecture, which means which is also called disaggregated computer and storage architecture. As shown in this figure, you will notice the computing resources, which is a VW here, is isolated from the data storage. So you will notice that we have many computing resources here. So from the perspective of the computing resources, they will see a global shared pool, which is a data storage layer. So which means all of the data in this pool can be shared across all of the computing resources. So under this architecture, it has three major advantages. First, it has better elasticity because the computing resource and the storage can, because they are isolated, right? So they can be scaled independently according to the demand for the resources. Like if we want to more computing resources, then we just add more computing instance. If we want to, we have more data, then we can expand our volume for the data storage layer. So this is the first advantage. The second one is has better scalability. So because the data can be shared, so in theory, we can scale out to utilize as much computing resource as possible. So this is the second advantage. And the last one is it's more user-friendly for the user here. It means a cluster manager, because the manager don't need to worry about the data persistency, the data replica, and the data sharding, and all of these things can be delegated to the data storage. For example, we can utilize HDFS or even Amazon S3 to store those data. Of course, there is no silver bullet. Every architecture has its pros and cons. So honestly speaking, this disaggregated computing architecture, storage architecture also have its advantages. For example, because the computing and the data storage are separated, right? So it means we have extra latency for the remote access. So this is a introduction. This is a pros and cons for this new architecture. So people may want to ask, because both architecture has its pros and cons, then how do we choose a correct or proper architecture for my own case? Here, I try to compare the two architecture from four dimensions. The first dimension is environment. So in the on-premise cluster, and so in this case, the hardware resource is is relatively stable, like because you cannot increase or decrease your hardware resource very frequently. So in this case, you can consider the shared lasting architecture. But in public cloud, we can. I think the biggest advantage of the cloud is its very good elasticity. It can scale according to the user's demand, right? We can add some more instances at any time, and those instances are charged by hour or even fine-grained granularity. So means in the public cloud, we should have better elasticity to utilize the resource more efficiently. So in this case, you should consider the shared everything architecture. And the second dimension is performance. I already mentioned the shared nothing has extremely good performance. So if you are very sensitive for the performance, you should consider this one. But if you but share everything not means it don't have good performance. You still can have good performance, but it will have some. If for the cold data access, you must tolerate some minor downgrade. This is also one challenging, and I will introduce how do we improve it later. And the third dimension is the workload. So imagine if the workload is evenly distributed, like at any time you can utilize your resource fully. You can fully utilize the resource. There is no waste. Then you can consider the shared routing architecture. But if you your workload has some spike, like in the peak and off-peak pattern, then you should consider the shared everything architecture, because you need to scale up or scale down very efficiently to make your resource utilization, to fully utilize your resource utilization or save your money. And the last one is from the user's domain knowledge. So using ClickHouse, it need some expert on need strong background or domain knowledge on the operation or maintenance of this cluster. But in the shared everything, because you can dedicate some challenges like storage challenges to some existing systems, so it can don't require so strong domain knowledge. So that is some basic guideline for how to choose different architectures. Then let's take a look at our new system. How do we implement it? So there are three objectives before we start this project. We want to support the disaggregated computer and storage architecture natively, because as we already mentioned, this architecture has better elasticity, so we can utilize the resource more efficiently in the cloud. And utilize the resource more efficiently, which means we can save more money for the users or even for ourselves. And the second is objective is containerization. We want to make our all computing resource in containers, and we can utilize some container orchestration platform like Kubernetes to help us to manage our cluster, like scanning and auto failover, something like that. And also the containerization is also a major trend in currently. A major trend always means better ecosystem. Imagine if we want to extend our system to different cloud providers, or like Amazon or Azure, and we don't need to care about the lower level environment of this system. And if the Kubernetes is standard, then we can easily extend our system to different environment. And the last one is we hope our system can be more user-friendly. So if you have some experience on using ClickHouse, you must know you need to, for the data replication, you must choose a replicated merge tree for the, so to query the data in different shards, you also need to create a distributed table. So we want to hide all of these things to the users or even cloud manager, and to make them to use make our system more user friendly. So this is the three objectives. Then by taking those objectives, let's see how we implement our system. So first we do some abstraction on our system. We split our system to three layers. The first layer is a cloud service. So user will directly communicate with this layer. So we must guarantee it's always on, because user can collect it at any time. And the second layer is the virtual warehouse layer. So it's the virtual warehouse here. Actually, just it means our computing resources. So you can imagine we have many Amazon EC2 here and something like that. So this is the second layer. It's responsible for the computing. Then this layer is on demand, so which means we can scale up, do the scaling according to the user's requirement or the demand. And the last layer is data storage. So the data storage layer is to store the data here, and it can be expanded according to the data volume. And let's go into next part, and we can have let's take a look more details in our system. And this is a overview of the all components in our system. And because there are many components, so here we only need to care two parts, which are shown on the left part and the right side. On the left side is the computing resource. The computing resource here is just the server and the workers. So the users will directly send the queries to the server, and after the server accepts the queries, it will do some scheduling on those queries and schedule some those execution those subquery or some tasks to the different workers. So here we have different kind of workers: the read worker and the write workers. The read worker, which means it's mainly responsible for the select, and the write worker is mainly responsible for the insert. Actually, by having this disaggregated architecture, we can even have more kind of because the workers can share all the data in the storage layer. So it like in theory, we can have some more kind of workers, like we can have some dedicated workers for background tasks, like merge task. Merge task is also a concept from the ClickHouse. And yeah, this is a computing resource. And on the right side, I want to highlight two parts. It's the metadata and the data. The metadata here is which in ClickHouse it's a part. So you can imagine the part, we store the part in a distributed key value store. And for the data belongs to the actually data of this part is stored on a shared storage. The shared storage here can be like HDFS, A3, and other more distributed storage systems. So let's yeah, this is an overview of our new system. And let's take a look some more implementation details. First, let's have a look at how query is executed in CNSH. So for select query, which means read, then it mainly consists of 3 steps. When the CNSH server receives a query from the client, it will get the metadata from the catalog, which is the part, or which is the part, get the part from the catalog, and then the second step, the server will distribute the metadata to different workers, and then it will send the queries to those workers to execution. Then for each workers, after it receives the subquery from the servers, it will perform the part read from the virtual file system and perform some computing. And then after it's finished the computation, it will pass back the result to the server, and the server will do a final aggregation and send the final result back to the client side. So this is basically how a read query works in CNSH. Then for the write query, actually it's quite simple. You can imagine it's a reverse of the read. So first, when the server receives the like insert SQL, it will directly forward to a write worker, and the write worker will write the data to the virtual file system. And once the data is write to the virtual file system successfully, then it will commit those part to the catalog side. Then after that, then this insert query complete, and we can send back the success, tell the client side that your insert query is executed successfully. Yeah, it's quite simple. And that's how read query and the write query works in CNSH. And so in CNSH, you will notice the user don't need to be aware of how the data is replicated and how they are be sharded. All of these are transparent, and the CNSH will automatically do everything for the user. So user only need to send the query to the server, and the server will automatically do some scheduling and execution and for this query and send the response to the workers to the client side. And also at the beginning, I mentioned the new architecture has some disadvantages, like the remote accessing have some extra performance. So it's one of the challenges we have met in our system. So for this, to fill this performance downgrade, we utilize the cache to fill this gap, and also as a developer, because the hardware resources are developing very fast, and currently we already have a high performance network, and in near future the bandwidth will become larger and larger. So the performance gap will be reduced further, with the development of the hardware. Then from the software, from our system in perspective, we utilize the cache to further improve the performance for the hot data. Like we have the metadata cache as well as the data cache in different components. Like we have the metadata cache in server side, and we have the data cache in the worker side. I will introduce more later. And also the second challenge is because we changed our architecture. So instead of have the storage on local machine, now we have a global shared data storage pool. So which means we have some extra overhead in managing the data in this global pool. And so I will also introduce it in the following slides. So first, let's take a look how we leverage the cache to fill the performance gap under this new architecture. So we have the metadata cache in our server. So we have the table and the part level cache in CNSH server. Then if the cache can be hit locally, then there will be no remote access. So in most cases, especially for the hot data access, then there will be no remote access overhead, because it can be get from locally. And the second layer is the data cache. Then we have the part data cache in worker side, and we utilize the memory and the disk of the worker resources to store those cache. So after we in our production, and we found the CNSH can have similar performance as ClickHouse by leaving this cache, because most of the query have some skill on, not all the query will access I think more than 90% of the data will access some a small portion of the data. So which means by leaving this cache, we can hit almost hot data in memory. Then we don't need to fetch those data remotely. And then let's take a look how we manage our data in the global pool. So for the data itself, we simply utilize the existing distributed storage file system, storage system like HDFS or Amazon S3 to management. So we don't need to worry about the persistency and the replication and the sharding issues. We can only we just use it. However, because we change it's a global shared pool, so we cannot directly store those data like ClickHouse into our in the global shared pool, because we know that by default ClickHouse store the columns by using a separate file. It means if we have a lot of columns, then it will lead to huge a lot of small files. And we know like for example, if we are using HDFS, then the small file, if we have too many small files, it will hurt the performance. So instead of store those columns separately, we use a compact data format for our new architecture. And also, in order to support a different environment, different cloud, we need to define do some abstraction at the file system layer, and we need do some abstraction. We need to have a virtual file system abstraction. So after that, we can support a different kind of backend storage system easily, and we can also extend to support more storage systems more easily. Like we can support Amazon S3 and HDFS and Azure and or even any cloud object store, some more. And the second data management is for the metadata itself. And yeah, well, I will. So in the next, I will introduce more about how do we do the metadata management. So for the in order to manage our metadata more efficiently and more properly, we utilize transaction to help us to do this management. And also the transaction here, we need to consider the distributed transaction, because we know we also have tons of metadata. They cannot be stored in only one server. We must store in a distributed environment. So that is why we need the distributed transaction support. And also we need to have some ACID property to guarantee our data property. For example, let's take a look at example. If we don't have the ACID support, what will be? For example, we know this is a process of how the insert works in ClickHouse. We know if we have a large amount of data, then all of the data will be translated to different parts and write to the storage system. And those parts you will notice because they will be write into different nodes. So how do we make sure all the nodes, how do we make sure all those parts can be seen at the same time? So it's challenging. If we don't have the ACID guarantee, for example, if some parts write into our system successfully, then they will become visible. So the other users may see some partial data, which is not good. So after we have the ACID support, we can guarantee all of the data can be seen at the same time. Otherwise, nothing can be seen. And additionally, if the failure happens during the insert process, the partial data will also not be visible, and our system will automatically clean those partial data from our system. So after have the ACID support in our system to do the metadata management, our system can guarantee better data quality. And then let's take a look at the because the metadata will be updated in parallel. Like the users from the user side, they may update the same data at the same time, right? So we must have the concurrency control to make sure the data is updated correctly. So we utilize some logs, and here we develop some fine-grained log to support this feature. So we have DB table and partition and part layers. So for different queries, we can use different kind of log to guarantee the correctness, and at the same time, it will not sacrifice the concurrency a lot. And in order to further improve the concurrency, we also propose the multi-version multi-version concept for our metadata. Imagine like if one user is updating one part, so we will not do the in place updating. Instead of doing the updating in place, we will generate a new version for this part. So the old part will not be changed. So the read query will not be impacted because they can still using the old part for the whole life cycle of this read query, and the writes will not impact the part. So by doing this optimization, and our read will not be impacted or even blocked by the write, which means we can have better performance under the heavy concurrent read and write scenario. This is the second optimization for the metadata management part. Yeah, I think that is almost all for our introduction for our new system. And then I will list some future works we plan to do in the near future. And because currently in ByteDance, most applications are still running in the ByteHouse internal ClickHouse. So we are doing the migration. So we plan to migrate more and more applications to CNCH cluster. And secondly, we plan to support, in addition to the ClickHouse SQL, we plan to support the ANSI SQL. And the third is because after we're having the virtual warehouse abstraction, and which means we can support more and more storage backend. And like currently we are supporting HDFS, but in the near future we plan to support more like A3 and other more kind of storage systems. Yeah, let's conclude our introduction, our presentation today. And I think there are 3 takeaways. And because CNCH utilize new architect, the disaggregated computing and the storage architecture, so it can utilize the resource more efficiently. And secondly, it's by leveraging the cache, then CNCH can still achieve competing performance as ClickHouse. And then lastly, by using CNCH, the users can have lower operation and the management. I think it's good news for the SRE or even DevOps. Yeah, I think that's all for my today's sharing.
Okay, thank you, Zhao Jie. Thanks for your very enlightening and inspiring presentation. And this part, it is our question and answer session. And it seems that we have a few questions on the chat box. And Yang, and are you prepared? And you could pick some questions from the chat box and give us your answers.
Yeah, do you mute it?
I think Yang are muted. You should unmute your speaker. Yang.
Yeah, you are muted.
Okay. Yang, you should unmute yourself. Yeah.
Yeah. Okay. Sorry, what was the question?
I think there are 4 questions in the chat box. The audiences want to know the similarities and the differences between ClickHouse and Druid or some Kylin. I don't know how to pronounce this word, Kylin or Kylin.
Okay. Okay. So okay, I don't have the comparison result on my hand right now, but yeah, I think there are like plenty of benchmarks online to see, because Killing and Druid also they are also very popular. But one thing to add is like it's not really fair to compare head to head between ClickHouse and Killing. Since Killing is a MOLAP engine, so it involves the pre-computation, just like I mentioned in my sharing. So it will involve like pre-computation of your data set. So actually the query result is not a true real-time result. For example, like if you have data, like streaming data coming in continuously, Killing actually can only give you a pre-computed result, which is not like real time. So the new data coming in will not be counted into the calculation. So Killing this kind of MOLAP, which sometimes can reach relatively higher QPS with relatively fixed query patterns. But ClickHouse can do real-time calculation, like a true real-time calculation. That's what I want to answer for this question. Yeah, for the detailed benchmark result, probably you can do a quick search online.
Yeah, are there any questions you want to pick from the chat box and answer? Have your answer?
What is the next?
I think the next one may be how to use bitmap optimizations.
Okay. So for bitmap, actually, we've gone through like several iterations of bitmap optimization for our CDP platform. So we start with change of the table schema. We try different ways of of mapping user tags to the user ID. And then after that, we still feel it's not fast enough. So we tried some parallel computing for the bitmap operation, things like and union intersect, those kind of operation. But it's still not ideal. So the reason why it's not ideal is because sometimes the user ID is quite sparse. So it cannot be stored very efficiently in a bitmap. In a 64, we use like 64-bit bitmap. So if the user ID is sparse, it cannot be continuously fit into the bitmap. So it causes the parallel computing not that ideal. So we take it further into encoding, a bit engine, which is in-house developed encoding for the bitmap. So after encoding, the data can be condensed and processed more efficiently. That's a rough history of bitmap optimization. But for the details, I think if we have like a lot of interest in this topic, maybe in the later sharings, we can consider add this into a separate independent topic. Yeah. Okay. Then I believe the PowerPoints for this sharing will be shared later. I'm not sure. Can you confirm?
Okay. How about Ian have a rest and welcome Zhao Jie to pick up some questions and give your answers.
Okay.
I think
the first one is how to split, right? Is this one?
Yeah, I think there are a question named how do you split compute and storage layer in Kubernetes? I don't know whether we have the same question here.
Okay. Yeah, I think that we don't really we actually this split is not related to the Kubernetes. Like even without Kubernetes, we can also split the computer and the storage. So the computer, you can imagine it's like the EC2 instance, and the storage can be the S3. So they are not really depend on the Kubernetes, but we can utilize the Kubernetes to manage our computing resources. And we are also doing so. to utilize the Kubernetes to managing our computing resources. The next one is, do you implement a separate database engine? Yes, in the new architecture and in the new context, we implement a new database and table engine to support the new architecture. Because you can imagine all the concept globally instead of unlike the ClickHouse, the engine is locally. So in the new architecture, you can imagine all the context when you talk about it. It's the global. It can be shared globally. So we need to do some support on or changes by developing a new engine. Slides. Yeah, I think the host will share more about whether the slides or the video will be shared or not.
Yes, we will upload this video on YouTube or some official accounts.
Okay. So it can share, right?
Yes.
Okay. Yeah. CNCH, a supervisor which manages fleet and standard which manage fleet of standard ClickHouse server. Supervisor. I think this question is hard to answer because it's not quite clear. Of course, CNCH server will have some extra role, like especially for the part scheduling, part allocation, and query scheduling. So if you define this as a supervisor, then the answer is yes. The architecture difference between Snowflake, I think the architecture is the same. We both using the disaggregated computer and storage architecture. But the implementation details, there are a lot of difference. Because we are still developing on top of ClickHouse then to utilize and we also want to achieve the computing resource performance as ClickHouse. So we did some special changes or implementations, even we are using the same architecture. How we support ACID? Yes, because time is limited, I didn't touch too much detail about the how do we implement the ACID for the metadata management. But simply speaking, we are using a distributed key value store to store those metadata. After we did some customized, or we did some special optimizations for the CNCH in context. So we are not simply using it, but we did some extra layer on top of it and to satisfy our transaction or ACID requirement. For example, we cannot utilize the atomic directly provided by the distributed key value store because we have a massive data part and it has some the default key value store has some size limitations on the single transaction, so we cannot utilize it directly. Then we did some further development on top of it. I think this is for Yiyang, the ClickHouse server. I will see.
Hey, let me see.
Sims is for the ClickHouse or CNCH.
That is for the transaction.
Yeah, I think it should be related to the multi-version. Yeah, for the multi-version of the metadata management, we are not. Yeah, for this, we will not copy all data. We will do some incremental updating. For example, if you only update one column, we will only generate incremental update for those one column. So we are not copy the whole 10 gigabyte, 10 gigabit, or 10 gigabyte data.
I think the next one is for on my side.
Yeah.
Primary database, Postgres. Can I replicate only a few tables? Ping log to ClickHouse. Yes, sure. You can do. So first of all, you can do. You can only replicate a few tables in Postgres to ClickHouse and just only accelerate analytics related to that table in ClickHouse. But I think ClickHouse doesn't support Bing log for Postgres yet. But actually, we are developing something in-house for supporting this feature specifically. Yeah, but I think you can try to use some other data pipeline, try to solve the data syncing part, data streaming part. Yeah, after that, it's definitely doable. Yeah. Yeah, I think that's all for all the questions. Have we missed anyone?
The last one is the open source plan. Currently, I don't have the answer. Yeah, and we will, if we have some plan, we will update later. Yeah. But currently, not sure about this.
And
I think all questions has been answered.
Yeah. And it looks like we have covered all of those questions. And if you guys have more detailed things you want to talk with our presenters, we have a survey at the end of this webinar, and you could leave your address, contact address, emails, or things like that to leave your questions, and our presenters will answer your questions, and they will have a more discussion with you. And so before we end this meeting, Zhao Jie and Yang, is there anything you want to cover or to say something to the audiences?
Nothing from my side.
Yeah, Yang.
Just go and try out ClickHouse. That's all.
Yeah. Okay. And so thank you for all the presentators today, and thanks for attending this webinar. And we appreciate you all being here. And this webinar is being recorded, and we plan to upload the video on YouTube or Twitter or something else on the official social account. And thanks. Bye-bye.
Bye.
Bye-bye.